Welcome to the Deep Dive, the show where we unpack groundbreaking research, really get into the weeds, and give you the core insights. Basically, we want you to walk away not just knowing about something, but really getting it. And today, we're looking at something fascinating. It's a world where robots are starting to perceive things, well, differently. Not just seeing, but like sensing with incredible speed and precision. It's almost superhuman, you could say. Just think about, the applications already unfolding. Autonomous cars navigating busy streets, right? Making those split-second decisions to keep pedestrians safe.
Exactly. Or collaborative robots, cobots working right alongside people in factories. They need to be perfectly in sync, totally safe.
Yeah, and for that to work, they need more than just a vague idea of what's around them. It's not enough to know something is there. They need to know precisely where it is and, crucially, how it's moving. Like, right now.
Mm-hmm. And that brings us to this core concept, human instance segmentation, or HACE-IS. It sounds technical, but it's really about the robot being able to draw a sharp line around each individual person. Not just human detected, but this human and that human separately.
But the cameras we typically use, our conventional ones, they kind of hit a wall here, don't they? Especially for these really fast, critical tasks.
They do. They really do. The issue is fundamental. These cameras capture everything, all the time, massive frames of pixels, constantly.
Even if nothing's changing, like a static wall.
Even if nothing's changing, they generate this just enormous amount of data, which means slow processing, high compute costs.
Yeah.
It's often just not practical for robots that have, limited power processing on board. Think drones, small delivery bots.
Right. It's like trying to listen for a whisper during a rock concert.
Yeah.
You're getting way too much input you don't need.
That's a great analogy. And it leads to delays, latency, which is just unacceptable when safety is on the line.
Okay, but you said there's something new, a different approach.
Yes, exactly. And that's where things get really exciting. There's this different type of sensor called an event camera. It completely flips the script on how robots see.
An event camera? How does that work then?
Well, instead of taking snapshots, full frames, it works more like like our own optic nerve, maybe. It only reports changes.
Changes in what?
Changes in brightness at each individual pixel. So a pixel sits there, and if the light hitting it gets brighter or dimmer by a certain amount, bang, it sends out an event.
Just that one pixel.
Just that pixel, asynchronously. It sends a tiny packet of data. Where it happened, the XY coordinates, when it happened with incredible time precision, and whether it got brighter or darker, the polarity.
So no frames, just a stream of these little change notifications.
Precisely, a sparse stream. If nothing changes, there's no data. It's inherently focused on dynamics, on motion.
Wow. Okay, that is different.
And this is where our deep dive really begins. Researchers have taken these event cameras and built something called EventMASK.
EventMASK.
Yeah. It's a novel way to do that human instance segmentation we talked about, but using event data.
Yeah.
The goal, low latency, low cost, and avoiding all those bottlenecks of traditional cameras.
Okay, so our mission today is to unpack EventMASK, how it works, why it's potentially such a big deal for robotics, for automation, giving you that shortcut to understanding this cutting-edge tech.
Exactly. We'll get into the nuts and bolts, see why it's a significant leap forward. Hashtag the deep dive.
All right, let's dig into this human instance segmentation, or HIS. You said it's about outlining each person. Can you elaborate a bit more on why that level of detail is so foundational?
Absolutely. It's foundational because simple detection, just knowing a human is present, isn't enough for complex interaction. HIS provides that crucial next layer of understanding. It answers, where are the exact boundaries of this specific person right now? And where are the boundaries of that other person over there, maybe even partially hidden?
So it distinguishes individuals.
Yes, precisely. It allows the robot to perceive people as distinct entities, each with their own space, their own potential movement. Without that, you can't have safe navigation around multiple people or truly coordinated human-robot teamwork. It moves from just seeing to actual spatial understanding of individuals.
Okay, that makes sense. And you mentioned autonomous driving earlier. How critical is HIS there?
Oh, it's absolutely paramount. For pedestrian safety, you need to accurately identify and track each individual. Think about a busy street crossing.
Yeah, people moving everywhere, different speeds, maybe someone stepping off the curb unexpectedly.
Exactly. HIS allows the system to track that specific person stepping off the curb, predict their path, and react appropriately, differentiating them from the person still waiting or the cyclist approaching. It needs to handle clutter, changing light, partial occlusions.
So it's not just avoiding blobs, it's understanding individual trajectories.
Precisely. And the precision directly impacts reaction time. Milliseconds saved because the system knows the exact boundary of a person can be the difference between safety and tragedy.
And in collaborative robotics, those robots working side by side with humans.
Same principle, different context. Imagine a robot handing a tool to a person. His ensures the robot knows the exact dynamic location of the person's hand and arm, allowing it to perform the handover safely and efficiently without collision.
Right, it needs to know where the person is, not just generally, but specifically where their limbs are moving.
Exactly. It enables fluid, safe interaction. It prevents accidental contact, builds trust, and makes the whole collaborative process work. And then you have applications like surveillance.
Being able to track specific individuals in a crowd.
Yes, providing real-time threat assessment by delineating and following specific people with high accuracy. Again, it comes down to distinguishing individuals within a complex scene.
So across the board, driving, manufacturing, security, this precise individual outlining is the key capability.
It really is. It underpins the next level of intelligent robotic behavior in human environments.
Yeah. But as we touched on, conventional cameras struggle. You mentioned the data volume. What else makes them fundamentally ill-suited for this hero's task, especially on, say, a mobile robot?
Well, beyond the sheer volume of data from capturing full frames constantly, there are several linked issues.
Okay.
First, that massive data leads to computationally expensive algorithms, processing millions of pixels every 30th of a second just to find and outline potentially only a few moving people. It's hugely inefficient.
So it needs powerful computers, lots of energy.
Exactly, which is often a non-starter for mobile robots running on batteries. Then there's the latency. Because they work in frames, there's that built-in delay, 33 milliseconds at 30 frames per second, before the system even starts analyzing the image.
And in that time, a person could have moved significantly.
Precisely. For fast interactions or safety-critical moments, that built-in delay is a major problem. You need near instantaneous reaction.
Okay, data volume, computational cost,
Yeah.
latency, anything else?
Yes, a big one. The reliance on deep learning for the current state-of-the-art HAS on conventional cameras.
Right, you mentioned these deep neural networks. They're powerful, but
But they come at a cost. High computational demand, significant power consumption, as we said. But also, crucially, they require massive amounts of labeled data for training.
someone has to actually draw those outlines on thousands and thousands of images.
Exactly. Instance-level annotation, drawing precise boundaries around every single person and frame after frame. It's incredibly time-consuming and expensive. It's a huge bottleneck for developing and deploying these systems.
So it's this perfect storm. Too much data, too slow, too power-hungry, and incredibly expensive to train. It really does sound like we need a different approach.
Which brings us back to event cameras. They seem almost tailor-made to address these specific bottlenecks.
Okay, let's dive deeper into these event cameras. You said they work more like our eyes, sensing change. How exactly does that mechanism translate into advantages for robotics?
Right. The core idea is that each pixel acts independently and asynchronously. It's not waiting for a central clock to say capture now. It fires only when its specific light level changes significantly.
So E, D coordinates, time t, and polarity pi brighter or darker. That's the event tuple.
Exactly, ESDET pi. And that stream of tuples is the camera's output. This leads directly to several huge advantages.
The first one you mentioned was sparsity.
Yes, sparsity. This is probably the biggest win. Because events are only generated by change, if large parts of the scene are static, no data comes from those parts.
So a robot looking at a mostly still room isn't constantly processing the walls, the furniture,
Okay.
only, say, the person walking through.
Precisely. The sparseness of event data significantly reduces the computational overhead. You're inherently filtering out irrelevant static information at the sensor level.
That sounds incredibly efficient compared to processing millions of pixels regardless.
It is, which leads to the second advantage, asynchronous processing. Events are handled as they arrive, not in batches tied to a frame rate.
Meaning lower latency.
Much lower latency. We're talking in the order of milliseconds. The system can react almost instantaneously to changes because it's not waiting for the next frame to be captured and delivered. Think collision avoidance, that immediate reaction is critical.
Yeah, no 33 millisecond built-in delay.
None. Then there's high temporal resolution. Because each event has that super precise timestamp, tie, you get incredibly fine-grained information about when things happen.
So you can track fast movements much more accurately.
Exactly. You can understand motion dynamics, estimate velocities, accelerations much better than inferring it from discrete frames spaced relatively far apart in time.
Okay. Sparsity, low latency, high temporal resolution, and I assume less power consumption.
Absolutely.
Probably.
Less data generated means less data to process, which means reduced power consumption. For mobile robots relying on batteries, this is huge. It means longer operating times, smaller batteries, less heat generated.
So if you tie this all together, the event camera's sparse, asynchronous nature seems to directly counter the main problems of conventional cameras for dynamic tasks like HIS.
It really does. It offers a fundamentally different, potentially much more efficient pathway for perception in resource-constrained real-time robotics.
But it also creates a new challenge, right? You don't have nice, neat frames anymore. You have this cloud of event points scattered in space and time. How do you make sense of that to actually find and outline individual humans?
That is the million-dollar question, and it's exactly what EventMASK is designed to answer.
Okay, so EventMASK. This is the system built specifically for this event data. How does it tackle that challenge of turning this sparse cloud into meaningful instance masks?
Well, the core philosophy behind EventMASK is to embrace the nature of the event data, not fight it. It's designed as an asynchronous, semi-supervised, non-deep learning-based method.
Hold on, non-deep learning. That seems counterintuitive. Isn't everything deep learning now?
It often seems that way, but in robotics, especially with sparse data, non-deep learning solutions are preferable due to their low computational complexity. Deep learning models often thrive on dense data, like frames. Applying them directly to sparse event streams can be overkill or even inefficient.
So simpler might actually be better here.
In this context, yes. Traditional non-deep learning methods struggled with His on noisy, dense frames because the features weren't distinct enough. But the clean, dynamic, focused information from event cameras, it makes these computationally lighter methods viable again. They can effectively extract the necessary patterns from the sparse event cloud without the massive overhead of deep networks.
Okay, that's a really interesting point. So EventMASK leverages this efficiency.
Yeah.
What's the process? How does it go from raw events to masks?
It's structured as a clever three-step pipeline designed to process these sparse raw events asynchronously.
Step 1.
Events to human segmentation. First, it needs to filter the incoming event stream. Which events are likely from a human and which are just noise or other background movement.
Sifting the signal from the noise. Got it. Step 2.
Segmentation to instance mask. Okay, now we have a cloud of human events. But if there are multiple people, this step figures out which events belong to which person. It separates the cloud into individual clusters, one for each human.
Ah, the actual instance part. Okay. And step 3.
Instance mask parameter update. This is maybe the most innovative part. People move, right? So this step continuously adjusts and refines those individual masks over time, keeping them accurate as people walk, turn, gesture, whatever. It ensures the masks track the dynamics properly.
So filter, cluster, and then track and refine. Makes sense. Let's break those down. All right. Step 1, events to human segmentation. Filtering that stream. You compared it to finding gold flakes in a river earlier. How does EventMASK actually do the sifting? What's it looking for?
It relies on extracting smart spatiotemporal features from the events. It needs to understand both where and when things are happening and the patterns involved.
Okay, what kind of features?
It uses a few key ones. There are temporal features that look at things like the rate of events at a pixel, and importantly, those polarity probabilities we mentioned, P plus and P. Remember, the probability of a pixel getting brighter versus darker.
Right, the statistically robust indicators of change type.
Exactly. Then it combines space and time with a spatiotemporal feature called spatiotemporal entropy. You can think of this like measuring the activity level or dynamic buzz in a small local neighborhood of pixels over a short time window.
So if an area has lots of events firing close together in space and time, it has high entropy.
Precisely. High entropy suggests coherent motion, like a person moving, rather than just random, isolated noise events scattered around. It gives a holistic view of the interplay between object and their movement.
Okay, it has these features: motion rate, polarity bias, local activity level. How does it use them to decide human or not human?
This is where the spatiotemporal event classification module comes in, and where that non-deep learning efficiency really pays off. It feeds these extracted features into a support vector machine, SVM.
An SVM. That's a more classic machine learning technique, isn't it?
It is, and it's chosen very deliberately here. SVMs are renowned for its efficiency even when presented with fewer samples, which is perfect for sparse event data. They can also achieve high accuracy with a lesser number of labeled events needed for training compared to deep learning monsters.
So less training data needed, less computation during operation. Sounds ideal.
Exactly. It's trained once on a relatively small set of labeled events, human versus non-human. Then, as new events stream in, the trained SVM classifies each one in real time very efficiently. Its less compute classification enables us to identify human events as they unfold.
A really pragmatic choice. Using the right tool for the specific data type. Okay, so now we have a cleaner stream, just the human events, but maybe it's 2 or 3 people. How does step 2, segmentation to instance mask, separate them?
Right, this is the crucial step for getting individual outlines. And again, there's a very smart choice made here. It
Yeah.
uses an unsupervised approach.
Unsupervised, meaning it doesn't need labels telling it which event belongs to person 1 versus person 2 during training.
Exactly. The motivation is clear. The cost involved in instance labeling has been the motivation. Labeling events at the instance level would be incredibly laborious and expensive.
I can imagine. Painstaking work.
But the insight here is that the spatial characteristics of events encapsulate the necessary and sufficient information to separate them. Basically, the XY coordinates of the human events themselves provide enough information to cluster them.
So how does it do the clustering?
It models the spatial distribution, the XY coordinates, of human events using Gaussian mixture models, GMM. The assumption is that the events from each individual person form a sort of 2D Gaussian blob, or cluster.
Okay, so each person is represented by a Gaussian distribution.
Essentially, yes, a GMM is just a combination of multiple Gaussian distributions. The system assumes there are C humans, so it tries to fit C Gaussian distributions to the incoming human event data. Each Gaussian has a center, meet BIC, a shape, covariance and AUK, and a weight.
And how does it figure out the right centers and shapes for these Gaussians?
It uses a standard, powerful statistical algorithm called expectation maximization, EM. EM iteratively adjusts the parameters of the C Gaussians, their means, covariances, weights, to best fit the observed human event locations, maximizing the overall likelihood of the data given the model. It automatically discovers the distinct clusters.
So EM finds the blobs, and once it has these initial Gaussian masks.
They are propagated for future events. When a new human event comes in, the system calculates the probability that it belongs to each of the existing Gaussian masks. It assigns the event to the mask it most likely belongs to.
So it continuously assigns new points to the existing shapes, keeping the tracking going in real time.
Precisely. It's like refining those initial sketches continuously.
Okay, but people don't just stay in neat blobs, they move, change shape. This leads us to step 3, instance mask parameter update. This sounds like the key to making it work robustly in the real world. How does it keep the masks accurate over time?
This is really the core innovation, the novel method proposed to update the mask parameters. Its role is absolutely pivotal in ensuring that the masks remain aligned with the evolving characteristics of human instances, enhancing both accuracy and consistency.
So how does it update the mean, center, and covariance shape of each mask? Does it just recalculate everything?
Not exactly. That would be computationally expensive. Instead, it uses a constrained likelihood-based optimization. It updates the parameters, O plus C and O plus C, by maximizing the likelihood based on recent events, but with crucial constraints.
Constraints. What kind of constraints?
There are a few key ones. The first essentially enforces memory. It tries to keep the new mean, plus C, as close as possible to the previous mean.
So it doesn't just jump wildly based on the very latest events. It remembers where the person just was.
Exactly. It balances new information with recent history. It preserves the memory while still adapting. The other constraints focus on the covariance matrix, the shape. They encourage it to be as close as possible to a diagonal matrix.
Diagonal dominance. Why is that important?
Well, spatially, for a person's event cloud, you generally expect the spread in the x direction to be largely independent of the spread in the a direction over short timescales. Enforcing diagonal dominance reflects this assumption, making the shape estimation more stable and less likely to capture noise or spurious correlations between the axes.
Okay, so the math is basically saying, update the position and shape based on new data, but don't forget where you just were, and keep the shape estimate relatively simple and stable.
That's a great way to put it. The paper goes into the math using Lagrangian multipliers to combine the likelihood maximization with these constraints, resulting in specific update equations, like EQ14 for the mean and EQ17 for the covariance. The key takeaway is that these equations cleverly weigh the influence of past parameters against the information from current events, guided by those constraints.
It sounds like a very elegant balance between stability and adaptability, not just reacting, but learning and refining continuously.
That's exactly the goal, and why this update module is so critical for robust long-term tracking.
Okay, the design sounds incredibly clever, leveraging event data and smart algorithms. But the proof is in the pudding, right?
Huh.
How did EventMASK actually perform in tests? Did the researchers validate these individual steps and the system as a whole?
They absolutely did. They conducted extensive experiments, starting with validating the human segmentation module. Remember, that first step, filtering human versus non-human events using SVM.
Right. How did the SVM stack up?
They compared it against a whole suite of other classifiers, KNN, decision trees, random forests, even a simple multi-layer perceptron. The results, shown in Table I of their paper, clearly indicated the SVM's superior behavior, especially in terms of ROC-AUC score.
So it was good at telling humans apart from background noise.
Very good. And crucially, it confirmed the SVM's remarkable ability to work with an exceptionally minimal number of events. This strongly supports the idea that you can do this initial segmentation effectively with a cost-effective, non-deep learning approach when using event data.
Okay, validation for step one. What about handling an unknown number of people? The instance clustering step relies on knowing C, the number of instances, right?
That's a very practical concern. They tested this using the NUPITS dataset, where the ground truth number of people was between 2 and 4. They then ran EventMASK, telling it to look for more instances, anywhere from 4 up to 20.
What happened when they overestimated the number of people?
Interestingly, as shown in Table 2, when the specified number was higher than the actual number, the system tended to split background noise events into extra false clusters. But critically, there was no apparent deterioration of MIOU, the accuracy metric for the real human masks.
So it created some phantom clusters, but the actual human tracking remained accurate.
Largely, yes. The main downside was simply increased computation needed to manage more clusters. They also observed a trade-off. Specifying more instances tended to decrease recall slightly, might miss some marginal events, but increase precision. The masks it found were very accurate.
Meaning you can tune it based on whether you prioritize finding everything versus ensuring what you find is definitely correct.
Precisely. The right balance can be determined based on the specific requirements of the application. That flexibility is key.
Now, what about that innovative mask parameter update model? How did they prove its worth?
They did two key comparisons. First, they looked at re-estimating the masks completely from scratch versus just propagating and updating them using their proposed method.
So recalculate everything periodically or just tweak the existing masks?
Exactly. They varied the re-estimation window, Table 3. Unsurprisingly, more frequent estimation yielded improved performance accuracy was higher if you recalculated more often.
What?
But this improvement comes at the expense of increased computational cost. Full re-estimation is computationally heavy, with complexity roughly ONNCD3. The proposed propagation and update method is notably lower.
So another trade-off.
Yeah.
Top accuracy versus computational efficiency.
Yes. And this gives developers guidance. If compute resources are tight, use a larger update window. If accuracy is absolutely paramount and you have the power, re-estimate more frequently. The second comparison for the update model was crucial. Their proposed constrained update versus a much simpler averaging method, simple mask or SM update. This tested if their fancy math was actually necessary.
Was it?
The results in Table 4 were clear. The proposed model, using those constrained likelihood equations, consistently showed better performance in terms of recall, precision, and MIOU. It validated that the sophisticated mathematical design directly translates to better tracking accuracy compared to a naive update.
Okay, so the individual pieces work well, the design choices seem justified by the data. Now for the main event. How does EventMASK compare to the state-of-the-art conventional HIS systems using regular cameras?
This is where the paradigm shift really becomes apparent. Table V shows the comparison against heavy hitters like ULEV8 V8, MASK RCNN, MASK Dino on the Spider dataset.
And the results.
EventMASK demonstrated clear superiority in terms of latency and compute. We're talking GFLOPs, processing time. The difference is stark. Remember, conventional systems process fixed frames, say, 30 frames per second, meaning a 33 meters latency per frame just for capture.
Right.
In that same 33 meters window, EventMASK processed, on average, only about 600 events. Orders of magnitude less data, leading to drastically lower compute and near instantaneous processing relative to the frame-based systems.
It really is like comparing a sports car to a bus for certain tasks, isn't it?
Yeah.
The efficiency and reaction time are just in a different league.
Exactly. It's not just incrementally better. It's fundamentally different because it's event-driven, not frame-based. Figure 2 in the paper drives this home visually.
What does Figure 2 show?
The left plot shows efficient computing. You see the number of events processed by EventMASK fluctuating wildly, sometimes near zero, sometimes up to 50K in a 25 meters window, depending entirely on how much is happening in the scene.
It adapts its workload.
Precisely. Whereas the frame-based system always processes the full frame, nearly 500,000 pixels in their example, regardless of scene dynamics. This directly translates to substantial power savings for EventMASK, especially when things are quiet.
And the right plot.
That shows low latency. Event-driven processing offers timing resolution down to the microsecond or millisecond level. Frame-based systems have that inherent latency floor dictated by the frame rate 25 meters in their example. EventMASK can react far, far faster.
So the quantitative results really back up the theoretical advantages. Event-driven processing enables response capabilities that frame-based systems just can't match.
Absolutely. The validation confirms the profound benefits. Real-time performance, computational efficiency, and power savings, all stemming from that fundamental shift to event-based sensing harnessed by EventMASK's clever design. #tag outro.
Wow. Okay, so let's try and wrap this up. EventMASK. It's not just another algorithm for HIS. It's really a completely different way of thinking about the problem, starting right from the sensor.
That's the perfect way to summarize it. It takes the unique strengths of event cameras, that sparsity, that low latency, and combines them with these really well-chosen non-deep learning techniques and that innovative mask update system.
And the payoff seems huge. Low cost, low latency, low compute needs.
Exactly. And crucially, robust performance without needing that incredibly expensive instance-level labeling that plagues conventional deep learning approaches for this task.
Which makes it much more practical for real-world robots, especially mobile ones.
Definitely. More agile, more power efficient, more responsive robots. It opens doors for applications where traditional vision systems just couldn't keep up or were too resource intensive.
And is this the end of the road for EventMASK, or are they pushing it further?
Oh, they're already looking ahead. The immediate next step mentioned is extending it to work properly with moving event cameras.
Ah, so the robot itself can be moving while it's segmenting humans.
Exactly. That adds another layer of complexity, but it's crucial for truly autonomous mobile robots operating in dynamic environments. Imagine drones tracking people, or robots navigating busy warehouses alongside workers.
That really does expand the possibilities even further.
It does.
It makes you think, if robots can move from just seeing frames to truly sensing change with this kind of immediacy and efficiency, what does that unlock? Imagine robots that can anticipate our movements almost intuitively, collaborate with us seamlessly, navigate complex spaces with near-perfect awareness. How does that change how we interact with technology, how we design our spaces, maybe even how we think about autonomy itself? When machines can perceive us not just as objects, but as dynamic individuals, instantaneously and with such precision.
That's the provocative thought, isn't it? It suggests a future of interaction that feels much more natural, much more responsive, potentially much safer, too.
Something definitely to mull over. A fascinating glimpse into the future of robotic perception. Thanks for breaking down EventMASK for us.
My pleasure. It's truly exciting work.